First of all, I'd like to say it's good to be back home. I've been here 3.5 years with some old friends. It was fantastic. That's the best part of this whole trip. It's really nice seeing everyone. You know, being in the industry, there's certain requirements you have for inks and coatings, and that's like you need specific chemical and physical resistance properties, but that's just the card to play the game. The really way to get approved is color, and color matching is probably the biggest problem in the print industry, whether it's Reviewer, Flexo, offset, screen, whatever, digital, it's color matching. The print world has really got a better handle on color matching because it's controlled deposits and stuff, but we found in spraying, water-based spray onto glass, color matching is just needs a lot of help. And I said, sometimes you get a bottle, you don't know what it was printed with or what pigments used, or they give you an offset transparent ink printed on paper and you want to make opaque. So about a year ago, we started working, I seeked out our color scientist who knows nothing about printing or coating or glass. I said, perfect. He's going to use mathematics and scientific method and try to come up with a color system. So he's been working on it for a year. We want to believe the future, our goal, like Eric said in the morning, is color management, where you can efficiently read a color, you know, dispense it, and have your inventory control. I don't know, I go to a lot of shops and they want 40 pounds of color. By the time they get the color right, there's 60 pounds and there's 20 pounds in inventory. We go to some of the decorators, they have $1 million worth of extra ink, used off ink. Oh, we'll use it off. No one uses it off. And everybody has a special color. And the people you have, the bottom line of getting an approval for a job is color, because the designer or the brand owner, you know what they're like with the color. It's all subjective. And all our spectrophotometers on our head, we're not all calibrated. Everybody has different eyes. So I'm going to turn it over to our scientist, and he's going to, I think he'd be very excited about what we're doing.
Well, thank you, Bob, for that kind introduction. So when a company like Sun Chemical, you know, which has long experience producing inks for the printing industry, turns to producing spray coatings, you know, for bottles and glass, there's a lot of natural assumptions about color that carry over and inform our approach. And unfortunately, not all these assumptions are completely true, and often they aren't shared by decorators. So we'll look at some of them and we'll see how they affect glass decorating. So one assumption is that when coating manufacturers say color, we're talking about scientific coordinates, you know, like the, it's not, yes it is. I can see there on the left, like the LABs shown here that are typically read by spectrophotometers. And on the right is one of the most common spectros in the US that's called the X-Rite Exact. And now might be a good time to ask, how many of you in the audience use an instrument like this when you want to evaluate a color? Okay, so some do, some don't. So if you don't use a spectrophotometer, then most likely you're relying on visual assessments, you know, in which a human observer looks at two colors, he's got a sampler of proof, and he's got a standard, and he decides whether the colors are close enough. In most of the ink and coating world, you know, including the printing and automotive industries, color assessment is completely instrumental by now, so that it, you know, it uses spectrophotometric measurements are used exclusively. And it's often called by the numbers because it relies on technology. And the instrumental approach can be unnatural at first for many decorators and their customers, you know, who are accustomed to judging colors by looking. Oops, what did happen here? Did this, do I have to hit this? Oh, there we are. Okay, got that one off. So another assumption, and it's kind of similar to the one about spectros, involves viewing conditions and what's called metamerism. So an important result from color science, and it's really a very unintuitive result, is that two colors might appear identical in one kind of lighting, you know, say if you're outdoors in the afternoon in sunlight, but appear different in another kind of lighting, you know, say you're indoors under incandescent lighting. And that's why people in the printing industry only compare colors in a controlled lighting situation. By now they've settled on a light called D50 as their standard illumination. So special viewing boxes, like the one shown here, are used to make assessments about whether the color of a sample or proof is close enough to the color of a standard, you know. So is that bottle as good as a slide? Is that how good is that color match? You know, a printer would never make a judgment, a color judgment in his office under fluorescent lighting. And maybe I could have another show of hands here. How many decorators make sure that they're using controlled lighting when you compare two colors? So you use a light box like this and you choose D50, the same as the standard, the graphic standard? Okay. And another assumption is that most of the recipe formulation will be done by some computer software rather than by a human. So what you do is you make a database containing the color measurements of many mixtures. Maybe you take 0.5% of PR122 and 1% of PO34 in a polyurethane vehicle. And the software starts with a target color that's given by an L star, A star, B star, like we saw earlier, or a spectral curve, and then uses information from that database to estimate a recipe that produces that target color. And the best color formulation systems will get a good enough recipe on the first try, maybe 80% of the time or so. For decorators, an important fact to note is that the color matching software that's out there is primarily for traditional printing on paper or film, and it assumes that the substrates are flat. So already there is something of a gap when it comes to glass decoration, where a substrate, a bottle, maybe it's cylindrical, maybe it's a lot of times it's semi-irregular shape. And even though we have capable color formulation systems, it's not clear how well they'll transfer to glass decoration, nor what form the database should take to account for all the transparent translucent objects that occurs so frequently. So for comparison, let's take a look at how color matching works in the traditional printing industry. So if your customer, gives either a physical example of the color they want matched, or sometimes a virtual standard instead, to the printer. The printer passes that on to the ink manufacturer, asking them to produce an ink of the same color. The manufacturer measures the color, uses some formulation software to predict a recipe, a combination of pigments that in the right ratio to produce that color. The manufacturer mixes up a physical jar of ink in accordance with that recipe, and then a physical proof is produced on the appropriate substrate. And then a proof is just, you make a small print of it to see what it looks like. And you measure that with a spectrophotometer for numerical accuracy. And the perceptual color difference from the target can actually be calculated instead of just being observed. So there's a formula called DE00 or DE2000, which is the standard today. And that number may or may not agree with the human, your perception, the customer's perception, the manufacturer's perception of that color. But if that difference is small enough, so less than some agreed upon threshold, then the match is considered acceptable. And sometimes the match isn't quite right on the first try, so the software uses what's called batch correction to produce a second recipe, and occasionally even a third recipe is also needed. So this previous slide here shows some examples. So the target color of the standard is on the left, and then here are the match attempts. So we did, this was the standard, this was the first attempt, not quite good enough, this was the second, this one was gotten right away, and so on. So this color matching model for printing has been in use for decades, and it's long since proven its value. So it works for the manufacturer, the printer, and the printer's customers. So okay, why don't we just transfer it to the glass decoration field? And in fact, Sun Chemical has been trying to do exactly that, and probably other manufacturers have too. So there are some challenges though, which are serious roadblocks to a simple transfer. So an advantage in traditional printing, which makes the whole process run smoothly, is a controlled deposit of ink on a stable flat surface. So you need that to make consistent proofs, and many specialized devices, which tend to be just kind of miniaturized tabletop versions of printing presses, are used for just that purpose. And unfortunately, when it comes to glass decorating, there are no similar devices, standardized or otherwise, for proofing glass coatings. We've tried many options at Sun, from spraying with an air gun on a flat glass slide, to using bird applicators or wire-wound bars that are commonly used for printing inks, but consistency is proving to be a problem. And a further challenge is that there's no objective description as to when a color match is good enough. In fact, there's little appreciation of the advantages of objective tolerances. And the result often, it's a numerous back and forth between the customer, the decorator, the printer, the decorator, and the manufacturer, to finally get a match approved. And another common sticking point that's unique to glass decoration is how do you make a color measurement on cylindrical glass, like a bottle or a candle holder? If you're working with flat glass slides, color measurement is pretty easy. You put them in a transmission spectrophotometer. It's pretty rare, though, of course, to get a standard that's a flat glass slide. So a much more typical case is a cylindrical bottle. So to handle this case, Sun's built a prototype bottle measuring instruments, and here's just a schematic of it. So there's a part here that's inserted, it's not shown here, but it's inserted down the neck of the bottle, and it's got a light source coming through it. It's actually a miniature light tube. And then the light goes through the tube, and it goes through here. There's a light path to the receiver, and it's transmitted through the bottle's wall to the receiver. So from that, the transmission spectrum can be calculated. Now, I should hasten to add that while this works very well in theory, in practice there's a lot of troubles coming from an unexpected source, and that is the bottle itself. So here's a typical bottle on the left, and beside it is some high-quality laboratory glass. And if you view this orange stripe through the lab glass, as here, you see that it's curved because this is still a cylinder, but that the edges are very sharp and it follows a nice smooth path. Now look at the same orange stripe viewed through the bottle. Not only are the edges blurrier, but it follows a sort of a meandering path rather than a simple track. And when you look closely at the bottle, you realize that though it seems perfectly symmetrical, in fact it has a lot of bumps and hollows and many uneven sections. So when we measured the bottle with a spectrophotometer, it was found that all this unevenness led to unstable answers. So we measured in one position, we get one answer. We'd rotate it 20 degrees, measure again, and get a different answer, and so on. So here's some data. This first plot here shows the transmission spectra of the bottle that you just saw on the left that we measured 10 or 15 times. And for those in the audience unfamiliar with them, a transmission spectrum says what percentage of the light at each wavelength actually makes it through the glass. So at say 550 here, this is saying about 75%, 550 nanometers, about 75% of the light would make it through the glass. Now, as you can see here, these spectra are really spread out. The average DE00, that expression I mentioned before, between any two of them is about 1.9, which is really bad in most color measurement settings. And part of the problem here is just glass quality. So the second plot shows another 10 or 15 transmission measurements, but this time for that graduated cylinder that you saw on the right. Now, this is a laboratory tool made of high-quality borosilicate glass, and as you can see from the clear image of that orange line there, it's much more even and regular than the bottle. Its transmission spectra cluster together a lot more closely with an average DE of just under 0.5. Now, not great, but a lot better than before. So in practice, of course, we tend to get a lot more of the first kind of bottles as targets. And what we ended up doing was, you measure it, you rotate it, you measure it, you rotate it. You do that 10 or 15 times, then you take the average or the median of the measurements. And that got rid of a lot of the variation, but it's nowhere good as the kind of repeatability you'd get when you had a typical handheld spectra just measuring flat surfaces. So the difficulty of getting a good bottle measurement, it's a major roadblock for matching colors. And it's not just the coating manufacturers that are affected, but decorators too. Without a reliable way to measure bottle color, there's no quantitative way to say whether a match is good enough, or even sometimes, is your decorating process in control? You take a bottle, you spray it, take another one, spray it exactly the same. If you can't measure those and say what the difference is, how much control do you really have over your process? You don't know that. And there's a further issue that kind of arises, it's almost unnoticed sometimes with sprayed-on coatings, and that's the thickness of a sprayed layer. So suppose that a supplier, gives you a few gallons of some spray coating he's mixed up, as well as a proof he made by spraying that coating onto a bottle. You and your client look at the bottle, you say, okay, that color's good enough match for your target color, so you accept the shipment, and you spray it yourself using your equipment. And if you compare a bottle that you sprayed with a proof bottle, you might notice that the colors are a bit different, which seems impossible because they were both sprayed from the same batch of coating. And what happened is that the two sprayings produced two coatings of different thicknesses. Now, if the coating is opaque, the thickness doesn't matter much, as long as it's at least a certain minimum. But when the coating is transparent, thickness can make a big difference in color. So you can see some examples in this slide. So all three of these black spectra here, are from the same coating. but the same coating at different thicknesses. So this, this lightest one here, this is the top one here, that was 10 microns thick. This other one here was 20 microns thick, and this one here is 30 microns thick. And you can see what the difference that's making in the spectrum. And perhaps I could have another show of hands here. So how many decorators here in the audience actually know the thickness, the coats you spray, in terms of microns or mils, whatever unit you want to use? Okay, so a few of you, some of you aren't quite sure, a few of you do, okay. So at Sun Chemical, we found a mathematical way to, not exactly eliminate this, but at least to recognize when we're in that situation. So suppose we have a transparent color and we spray it at some thickness, maybe we produce, one of these here. Then we can use the Beer-Lambert law to calculate what the transmission spectrum would look like if we sprayed it, say, 15% thicker or 4% thinner, or whatever factor we want to consider. So we call this the virtual thickness correction because it's calculated rather than found physically. Now, instead of spraying a thinner layer, we could just as well reduce the concentration by adding some extra solvent or some water in our case, and then spray at the same thickness. So the important thing, though, is that we can identify this difference. Sometimes it's called the strength difference, and we can handle it numerically, avoiding a real-world holdup. So to sum up, then, there's a lot of challenges in color managing decoration, and they're going to need the collaboration of both decorators and coating suppliers, and probably and consumers too. We're encouraged with the algorithms and the equipment that Sun Chemical is developing to make the process more efficient and profitable. Ultimately, we'd like to establish in-house paint kitchens at glass decorating facilities to support color control on site. We've made a good start with what you've seen here, but of course there's still a long way to go. Any questions?
Yeah, you did mention it.
Yep.
Maybe I missed it. Did you mention anything about the color of the flint glass, particularly for translucent coating? Because that can certainly, affect the end color as well. Do you run into that problem?
Yeah. So what happens is when you want to measure the color of the bottle, or of the glass, you can't just measure the ink. You've got to put it on a glass slide, right? And then you say, or on a bottle. Let's say we put it on a glass slide, and then you put it in a transmission spectrophotometer and you shoot it through it. So what happens is if your glass is not completely clear, it's got a bit of color to it itself or a bit of darkness, that's going to affect those measurements. So what you actually have to do, if you're being really careful, and we've done this before, is you take the target glass if you can and you measure that, and then you say, okay, I know what my target color is, but I've got to recognize that there's this extra color being added by the glass, which wasn't in my proofs. So I've got to say that the color I want to match is my target color minus the color of the glass, and you've got to you give that color to the software to match, and then you put it on the not quite clear glass to do it. So you've got to make compensation for that.
Thank you.
Yep.
Can I ask you?
Yep.
So for glazes, coatings, or whatever, we tended to find that the smaller the aperture, the less accurate the spectrophotometer was for color
Yes.
matching. Is that what you see also, which makes it even more difficult for the bottle? Is that what you saw also?
Yeah, that's what we see. So, what's being talked about there, when you have a spectrophotometer, usually you shine a light and it bounces back, and you have an aperture that light goes through, and then it hits a sensor. And the bigger you make that aperture, the less variability there is in your measurement. And the reason is, what you're thinking about, a larger aperture is really built-in averaging. If you have a small aperture, say 1 square millimeter, you get one set of accuracy. But if you got say 4 square millimeters, that's like making 4 measurements and averaging them. So the result is you get a lot more consistent measurements. And yeah, we have found the same thing, and that's ordinarily for flat measurement, but yeah, you try to do this kind of measurement to that kind of, any kind of measurements. The smaller apertures are worse. You prefer a bigger aperture if you can get it. So.
Thank you. Anybody else?
Yeah, Wesley?
Well, very interesting. I'm just curious if you, with your experimental setup or your measurement setup, so you have an interior light source.
Yep.
And with clear bottles and translucent coatings, of course, what light makes it into the bottle and then back out towards the observer certainly does contribute to what the observer sees.
Right.
The major contributor to what someone visually sees on the outside of the bottle is a specular reflection coming off of smooth coating, right?
So that depends on how transparent your coating is. If your coating is very transparent, like stained glass in a church, there's really not much reflection coming off it. What happens though is, coatings kind of vary from completely transparent, still color, but completely transparent, to completely opaque. And then in between, you've got all these translucent shades where, okay, there's some light's getting through, but not as much. And yes, then you do have the problem of, you also have reflectance coming off, and that attributes to the appearance too. So when you take the measurement, usually what you do in printing is, for your ink, you measure it over white and black, you do reflectance measurements. So you're going to get reflectance off the surface of the ink, but you'll also get, some of the light's going to bounce through the ink, off your white background, through the ink again and come out. And then you've got a black background, so it's through the ink. Now there's very little reflection off the black background and what comes out. And the computer software are usually set up to have a measurement over white and a measurement over black. And the reason they do that is, there's reflectance and transmission going on here, and you want to see if you can catch both of them simultaneously.